Hi everyone, I'm Jeremiah Blanchard, and I'm going to talk to you about sets and maps. When we talk about a map in computer science, which we also sometimes call an associative array, we're talking about an array that lets us use any kind of indexing that we want, any kind of data type as the index. The basic function of a map is to associate some key, some index, with some value, something we're trying to store. And a key feature of a map is that each key has no more than one value associated with it. It could have no value, but it has no more than one. One good basic example of a map is a dictionary. The function of a dictionary is to associate words with definitions. In this case, the word is the key and the definition is the value. Actually, sometimes maps are called dictionaries for this reason. Map and dictionary are used interchangeably in many cases. One good way to implement a map is using a hash table. And in fact, in C++, the unordered map type in the standard library is based on a hash table. Here are some other examples where a map would be useful. We might use a map to associate a Social Security number with some patient's records. In other words, we could look up the patient's records by using the Social Security number. We might use it to associate a username with the user profile so that we could use the username to access that profile. And we could use an auction's ID to trace back to the seller in our records. These are just a few basic examples, but there are many other cases where we could use maps. Maps often come in two main variants depending on how they're going to be used. We have ordered maps, which are also optimized to allow us to iterate through the keys in order. In C++, a red-black tree is used to implement the ordered maps. And we also have unordered maps, and these give us better average case performance for random access in most cases. These are often implemented using a hash table. An ordered map would perform better if we wanted to list all patient records by the patient's name. An unordered map would work better if we're trying to get a user profile by using the username. In other words, if we're listing things in some specific order, an ordered map is going to be more effective, while an unordered map is going to be more effective for random access average case. With that said, most of the time ordered maps are built in such a way that they have much better access time even for random access than most list implementations. In this case, we have a very simple user profile structure composed of a name and an image file name. We allocate an unordered map, which will map a string, a username, to a user profile object. Then we're going to add two entries. At the index Mr. Ed, we'll add a new user profile for Edward Longshanks, who uses the image file lordbritish.png, and we'll also add a profile for the username Willwall that points to the user profile for Bill McWallace, whose image file is patriotflagpicture.jpg. Later, we'll ask the user for a username, and then we will display the image for the user that is typed. In this case, we place the username into the profile's map. It will yield a user profile pointer, and we will access the image file element of that user profile in order to show the image. A set data type is used to identify membership in a set. It's similar to a map, but rather than having a key-value pair, we have just a single element. Much like maps, a set can be ordered or unordered. A key difference between a set and a list is that in a list, you can have the same element appear more than once. However, in a set, if you try to add the same element a second time, the second addition will not actually add the element. An element is either contained, that is, it is a member of the set, or it is not. Some use cases you might see for sets are to hold a list of administrator usernames for a system. That way, if you add the username again, it doesn't create a new entry. You might use it to identify which items are in the inventory of a character in an adventure game, if a player can have no more than one of each item. And we can also use it to keep track of what features have been unlocked in an app. Sets also come in two main variants, as we mentioned briefly before. Ordered sets are easily iterated, much like ordered maps, and they also usually use a red-black tree underneath. And unordered sets, which also use a hash table, have better than average case performance for random access. For example, we might use an ordered set to list all administrator usernames in alphabetical order. We might use an unordered set to check to see whether a player has a particular item in inventory within an adventure game. In our example, we create a set of strings to represent the administrators of a system. Then we add two usernames to that set, Bob Jones and Ed Izzy. We then get a username from the user, and we check to see if that user is in the set. In this case, we're calling the find method of the set class. If the element is found, it will return an iterator pointing to that element. However, if that element is not found, it will return the end iterator. So, we check to see whether or not the end iterator is returned. If it is not returned, then the user is an administrator. And if the end iterator is returned, then the user is not an administrator. A variation on maps and sets is what we refer to as multimaps and multisets. A multimap maps a single key to multiple values, while a multiset keeps track of how many of a particular element have been added. Multimaps and multisets are not used nearly as frequently as maps and sets because they're a little more complex and hard to use. But there are some use cases. For example, you might use a multimap to connect a zip code to all magazine subscribers within that zip code. You might use a multiset to hold the inventory and the number of each item for something like an RPG. Like maps and sets, there are also ordered and unordered versions of the multimap type and the multiset type.